So here we are going to finish the rest of this section 4.3, looking at curve sketching. I know we already went over a couple of these examples in class, but given the circumstances, I thought I would run through them one more time. So for the first example, let me see if I can graph a polynomial function. How about x cubed minus 6x squared plus 9x plus 2. So depending on the specific type of function, there's different information I could look for. Maybe the y-intercept. I find that by setting x to 0, which just leaves me with the constant. Therefore, my y-intercept would be at the point 0, 2. Now, if I was to look for x-intercepts, well, I would be setting the y, or in other words, setting the whole equation to 0. In this case, because this expression doesn't factor, I don't have a simple way of solving this. So I'm going to see if I can create a graph without that information. So what's some other information I could find? What about, well, the first derivative. So f prime of x, let's see, that would be 3x squared minus 12x plus 9. So let me see if I can find the critical numbers. Critical numbers. So in this case, f prime of x is defined for all x's. So really I'm just looking then for where this quadratic is equal to 0. If I factor out the GCF of 3, let's see, I'd have an x squared minus a 4x plus a 3. And then can I factor that? Let's see. Looks like minus 3 and minus 1. That'd be x squared minus x minus 3x is minus 4x plus 3. So my critical numbers then would be x equals 3 and x equals 1. So then I have a couple options. I could use the first derivative test. So I would set up a sign chart. Remember, this is a sign chart for, well, the first derivative. I would indicate my critical numbers here. And then I would test the value. So I'm looking at the f prime of x, and I'm thinking, well, if I was to plug a big number in here, like, I don't know, 10. Let's see, if I was to plug a 10 in here, well, let's see. I'd have what? 3 times 100 minus 12 times 10 plus 9. Well, let's see. This is 300. This is 120. So this is going to be a positive number. Positive. If I was to plug in, say, a 2, let's see, that'd be, looking back at this, that'd be 3 times 4 minus 12 times 2 plus 9. So that's 12 minus 24 plus 9. That's less than 0. That's a negative. Let's see, what about f prime of 0? That should be the easy one. Well, if I put 0 in here, that would just leave me with 9. So that's positive. So then I have some information. So I guess I know, let's see, I know that this function is increasing where the first derivative is positive. So that would be on the interval -infinity to 1, and then again from 3 to infinity. I know it's decreasing on 1 to 3. That would be where the first derivative is negative. So based on this information, I could also reach a conclusion about local extrema or relative extrema. So let me see here. The function is increasing until it gets to 1. Then it starts decreasing. So I guess I would have to have a local max at 1, well, I'd have to figure out the corresponding y coordinate. So for that, remember, I actually have to look back at the original function and say, what is f of 1? So let's see, here's the function. So f of 1, let's see, that'd be 1 minus 6 plus 9 plus 2. So what is that? -5 plus 9 is 4, plus 2 is 6. So there's a local max. Let's see, what was my other value? So let's see. Increasing until I get to 1, decreasing until I get to 3, and then increasing. So I guess then I would have a local min at 3, okay, now again I have to find f of 3. So then I have to refer back to the original function here again. So, let's see, what is that going to be? 3 cubed, 27, minus 6 times 9, what is that, 54? Plus 9 times 3, 27 again, plus 2. So that's 54 minus 54, cancels, so just 2. So it looks like I have a local min at 3, 2. So that's one idea as far as locating the relative maxes and mins. Remember, the other idea was actually once I had found these critical numbers. So let's see, what were those? Those critical numbers I had found were x equals 3 and x equals 1. My other idea was I could actually use the second derivative test. So I guess in order to use that test, I'm going to need, well, the second derivative. So let's see, I'm looking back here. Here's my first derivative right here. So let me start then by finding my second derivative. So the second derivative would be what? 6x minus 12. So then as far as my second derivative test goes, well, what I'm doing there, remember, is I'm taking one of these critical numbers. So say x equals 1. And I'm saying, well, if I plug x equals 1 in here, let's see, what do I get? I get a -6. That's less than 0. So that means the graph is concave down at x equals 1. So that would imply then, if it's concave down at that critical number, that must be a local max. So let's see if that matches. Well, that's the same conclusion we reached up here. We have a local max then at 1, and then we'd still have to plug in 1 to get the corresponding y value of 6. So I can do the same thing here with, well, what about x equals, what was the other one? 3. Well, the second derivative at 3 would be what, 18 minus 12? What is that, positive 6? It's a positive number. So that tells me graph is concave up at x equals 3. So I guess that one would have to be a local min. So is that what we concluded? Yes. So I could use either the first derivative test or the second derivative test as far as finding relative or local extrema. So in any case, that part's done. We've got our local max, our local min. So what else can I do with the second derivative? Well, remember the other thing I could do with that second derivative is I could look at the concavity of the graph / look for inflection points. So my second derivative, well, my second derivative is 6x minus 12. So where would 6x minus 12 be? 0. Well, that would be at what? X equals 2. So there is my potential inflection point. So now I make my sign chart, but this time I'm interested in the second derivative. So my potential x value for an inflection point would be 2. So let me see, if I try plugging a big number in the second derivative, well, let's see, that's going to be like 600 minus 12, it's positive, right? Versus if I plug in like 0, well, it's negative. So then what does that tell me? Well, the graph has to be concave down then on negative infinity to 2 and concave up on 2 to infinity. So there's another piece of information. So I guess then I do have a change in concavity. X equals 2 is in the domain of the function. So then there is an inflection point. And that would be at 2, okay, now I have to find f of 2. So I'm actually looking for the point on the graph now. So I have to refer back. Let me see, where is my original function? All the way back up here. Okay, so what is f of 2? Let's see, well, 2 cubed is 8. Minus 6 times 4, what is that, 24? Plus 9 times 2 is 18. Plus 2. So what is this? 20 minus 24, negative 4 plus 8, is that 4? So it looks like I have an inflection point at 2, 4. Okay, so then let me see what I can do as far as putting some of this together and hopefully coming up with a nice sketch. So I have to just make sure to label everything. So let's look back at my first page. I guess the first piece of information I had was the y-intercept. So here's that, 0, 2. Let's see, I didn't find x-intercepts. Let's see, critical numbers. Okay, I have my intervals of increase and decrease. Okay, let's see, so up to 1, increasing. 1, 2, 3, decreasing, and then increasing again. Okay, let me see. I'll come back to that. Here are my local extrema. So those will be easy to include. Let's see. So I have a local max at 1, 6. 1, 2, 3, 4, 5, 6. So here's that, 1, 6. Local min at 3, 2. 2. What else did I find? Anything else here? I found the intervals of concavity. Okay, maybe I'll come back to that. Let me put my inflection point. Start with the points and then add in the intervals. So let's see. 2, 1, 2, 3, 4. There's an inflection point. Okay, so maybe let me start on the left. So let me see. So what do I know as far as my intervals go? Okay, so maybe I'll put this information together over here. I can refer to it. Okay, so if I start on the far left over here, let's see, I should be increasing and I should be concave down. So I don't know, maybe something like that, increasing, concave down. Okay, then I hit my local max, and then let's see, decreasing between 1 and 3, but I'm still concave down until I get to this inflection point. Okay, so decreasing, decreasing, I'm still concave down. Now here, this is the inflection point. So here's where it goes from the upside down U to the right side up U, something like that. Change in concavity. Okay, 3, 2 is my local min. Then let me see, that's where I start increasing again. And I'm going to stay concave up. So maybe something like that. And so there I have a little sketch of the graph of f of x. So, same idea. How about another function? So how about a rational function? Something like f of x is maybe x over x squared minus 4. Okay, so again I have to start putting together information. So maybe I'll start again with the y-intercept. That's easy to find. Let's see, f of 0, I would get 0 over negative 4. That's 0. So y-intercept at the origin. Let me look at x-intercepts. So for those, I have to set the whole function to 0. Then I would clear the fraction, just be left with the numerator as 0. So I guess, again, the only x-intercept is the one I already found here at the origin. What else? So we also look when we have a rational function at vertical asymptotes. So those arise where the function is undefined, or in other words, where the denominator is 0. So here I have a difference of squares. So that's a special form, factors x plus 2, x minus 2. Therefore, my vertical asymptotes would be at x equals negative 2 and x equals positive 2. What about horizontal asymptote? So remember, the horizontal asymptote is really telling us what happens on the ends of the graph for big values of x. So remember there, what we needed to look at is we needed to look at the leading terms. So you see how if x is a really big number here, this 4 is going to be irrelevant. What's going to dominate, I'm going to have this leading term in the numerator x and in the denominator x squared. So if I look at my leading terms, what I'm looking at here is x over x squared, which reduces to 1 over x. So now I'm thinking, well, what happens to 1 over x as x gets big, as x goes to positive or negative infinity, say? Well, if you think about this, if x is a huge number, I'd have 1 over 100, 1 over 1,000, 1 over 10,000. This is going to approach 0, right? So therefore, my horizontal asymptote in this case is y equals 0. And in fact, this would be the case anytime the degree of the denominator is more than the degree of the numerator. In other words, look back at the fraction here. You see how the degree of the bottom is 2, the degree of the top is 1, so the degree of the bottom is higher. Therefore, I know immediately the horizontal asymptote of this will be 0. That's because you can see the bottom of this fraction is going to be a lot bigger than the top for large values of x. So maybe this time I should let's start the graph here and let's add information to this as we go. So what did I find so far? Let's see, I found the x and y intercept was the origin. Let's see, I found the vertical asymptotes. There's x equals 2. There's x is negative 2. Then I found the horizontal asymptote. Well, that's just y equals 0. So I know on the ends, the graph is going to get close to that line. Okay, so then maybe I'll set the graph aside for a second here. And then we have to see what other information that we can find. So now maybe I'll start my differentiation. So let's see, the first derivative, I'll use the quotient rule. So derivative of the top, 1 times the bottom, and then minus the derivative of the bottom times the top over the bottom squared. So what is this? X squared minus 4 minus 2x squared? X squared minus 4 squared. So negative x squared minus 4 over x squared minus 4 quantity squared. Okay, there's my first derivative then. Okay, so let me find my critical numbers. Okay, so then I'm looking either where this guy is equal to 0. So that would mean, let me see, negative x squared minus 4 is 0. That'd be what? Negative x squared is 4. X squared is negative 4. Oh, okay, so actually there are no x values where f prime of x is 0. Okay, so if there are no x values where the first derivative is 0, I guess I know there are no relative extrema, no maxes or mins, right? Because those are places where the slope of the tangent line is 0. But remember, I had to also look at what about where is f prime of x undefined? So let's see, that would be where the denominator here is 0. Okay, so then I run into those same vertical asymptotes. But these are not going to actually be critical numbers because these guys, remember, these are actually vertical asymptotes. In other words, these guys are not in the domain of the function. But I would still have to say, well, let me see as far as increasing and decreasing goes, what happens as I move across those asymptotes. So here's my sign chart for the first derivative. So let's see, if I plug a big number into the first derivative, let's see, the bottom here is always positive. So really I'm just looking at the numerator. So I don't know, if I plug like 100 in there, well, this is going to be negative 100 squared minus, oh, actually, look at this. This guy squared with a negative in front minus a 4. This is going to be negative for all x. This whole quantity is squared. It's positive for all x. For all values of x, then, the numerator is negative. The denominator is positive. So actually, this guy is negative all the way across. So let's see, if the first derivative is less than 0 for all x, then actually, I guess I know this function is decreasing for all x in the domain. So I guess that would be from negative infinity to negative 2, from negative 2 to 2, and then again from 2 to infinity. So this function is decreasing on its entire domain. So what about the second derivative? So where's my first derivative? Okay, that's up here. Okay, so let me put the first derivative right here. Let's see, that was negative x squared minus 4. X squared minus 4 squared. Okay, this guy's going to be a little longer then. So quotient rule again. Square the bottom. X squared minus 4 squared squared, so power 4. Okay, derivative of the top, negative 2x. Times the bottom minus derivative of the bottom. Let's see, that's going to be 2 x squared minus 4 times 2x, and then times the top. Should have left more room here. Negative x squared minus 4. Okay, let me continue this, simplifying this guy. Well, I guess I can take out an x squared minus 4 from this as a GCF. An x squared minus 4 would be left. I'd have a negative 2x. Pulled out 1 power of x squared minus 4. There'd be 1 left. And then minus 2. This guy pulled out, so I have a 2x. And then my minus x squared minus 4. And then all that, x squared minus 4 to the 4th. Whew, this is the longer one, huh? So where are we there then? So let's see, I can cancel this with one of these. So what will that give me in my denominator? I'd have x squared minus 4 cubed then. We just go ahead and copy this down, I guess. So I'd have negative 2x, x squared minus 4, minus, well, 2 times 2, 4x, times minus x squared minus 4. Okay, it's not so bad, I guess. Let me see. Distribute negative 2x cubed plus 8x, and then distribute this. So that'd be plus 4x cubed plus 16x. Getting there. And I'd have x squared minus 4 cubed So then, okay, these guys are like terms, oh, so are these. So I'd have 2x cubed plus 24x over x squared minus 4 cubed. Factor out of 2x. That gives me x squared plus 12 over x squared minus 4 cubed. Okay, so that one was a little long, but now I have my second derivative. Okay, so then let's look at the question about concavity / inflection points. So I'm looking again, well, at my second derivative this time. So I guess, let me see where the second derivative would be 0. So if I set this guy to 0, let's see, this multiplies up, so I just have the numerator equals 0. But actually, if I'm looking at where the numerator is 0, the only place where the numerator is 0 would be here when x equals 0, because this factor is never actually equal to 0. X squared cannot equal negative 12, right? So actually, my potential inflection point would be at x equals 0. Now, I have to also consider where this guy is undefined. So again, this guy is undefined at those vertical asymptotes, -2 and 2. So remember, here I'm looking at the second derivative. Okay, let me see. So if I take a big positive number, 100, plug it in here, let's see. This is always positive. This would be 200, it's positive. 100 squared is really big, so I have positive, positive, positive. This is positive. Okay, what about something like 1? Well, let's see, it have positive. This is always positive. But 1 minus 4 is negative. A negative cube stays negative. So this guy would be negative. What about -1? Okay, -1. Well, let's see, I have a negative here. This guy is always positive. Let's see, -1 squared, well, that's +1. -4, though it's negative. This is a negative cube. This is still negative. So I'd have a negative over a negative. This would be a positive. And one more. What about a huge negative number? So I don't know. -100. Well, let's see. This would be negative. This is always positive. -100 squared, this is a huge positive number. -4, it's a positive number. So overall, this is a negative. Okay. So then, what can I write out then? So let's see, I guess this guy is concave down from -infinity to -2. And then again from 0 to 2. Concave up on, let's see, -2 to 0 and 2 to infinity. But actually, even though it changes concavity at -2 and 2, the only inflection point would be at 0, right? Because these guys are vertical asymptotes. They're not going to actually be points on the graph. But here at 0, the graph does change concavity. So I have an inflection point at 0, comma, what the heck is f of 0? So where is the original function? It's way back up here. Okay, so now I have to plug 0 in here. So that'd be what? 0 over 0 minus 4 is 0, right? So I guess my inflection point is at 0, 0. That's actually the intercept we found earlier, I believe. Okay, so do I have all the information? So then let me go back over to my graph, see what I have. So I have decreasing, I have concavity. Okay, so here was the graph. Okay, so starting on the left side, let's see here. The graph has to be decreasing until I get to -2 and concave down. So it's going to have to be something like this. Okay, let me see. Then in between -2 and 2, it's still decreasing. Okay, it's decreasing all the way across. So let me just look then at the concavity. So between 0 and 2, concave down. Let me see, concave up between -2 and 0. So that's the region I'm looking at now, in between -2 and 0. It's always decreasing, concave up. So it's going to have to be something like this. 0, 0 is the inflection point. So this is where it changes to concave down. Something like that. Okay, and then concave up again on 2 to infinity stays decreasing. So something like that. Looks like a nice final graph of f of x.